All right, I think this is working. Um, don't know where I'm hearing anything from. All right, I'm back. Anybody here? Okay, I see you there. So let me figure. I switched software, dude. It was just horrible. All right, so I'm gonna hide that because I'm not streaming to Facebook right now. Not streaming to Facebook. Stream chat viewers there. Microphone is there. My mixer. Hello. Okay, why is it? There was like a monitor. Is this it? Hello? That one? Oh man, I hit it the other day. Oh, it's gonna drive me nuts. Okay, so here's the camera. So Visual Studio is there. Um, oh, yeah, XSplit. Is that working? Gosh, why the hell is this not like work? Anyway, let me close this crap. It like worked exactly once. So video, Elgato, face cam. All right, so now I have to do cam control, camera hub, and so I'm here, camera, video, input. Do I have to zoom? Yeah, there we go. All right, and move that over a little bit and zoom out. All right, so that's the camera, noise reduction. All right, anti-flicker, so that's good. Save effects. All right, so that's good. So now here, so that's the video input, the video output. Yes, color frame, output size. Yep. All right, so that's good. And whoa, okay, that's HDR. Okay. Um, all right. Oh, I should get like a green screen. That's what I should get. All right. So anyway, and all right. So now we have Visual Studio, which is right here. No filter. Are you seeing this? Yes. All right. That's awesome. Okay, so that's this. So that's window capture. Um, so that's window capture. So this will be Visual Studio. which of course it's not finding. So you know what? I'm just gonna share the screen here. What is this? Oh, that's the chat. Okay. Um, so this is supposed to be here. Wait a second. Why is back? Okay, yeah. So this is up to down. Sorry, folks. So that's this, and then I'm gonna hide this, and I'm gonna add a source for desktop capture, and all right. Hey, is this stream coming across as 4K? Um, so these are, oh, here's what happened. I have to move this all the way down here. There we go. All right. 1440p. Yeah, it should be 344 or 3440 by 440 at 30 frames per second. So that's awesome. Okay. Yeah, so this is the other streaming software, and you can see at the bottom here, um, it's using my CPU, but it's using my GPU also. And like I can actually move my mouse and not lag. It's just better software. All right. Um, okay. So where were we? We were over here. Oh, there's an echo. Okay. Let's see. So here's the mixer. So I don't know what I did before, but I like turned on the monitor, like monitor style. Um, so I see two audio sources maybe. Let's see. So how about this? Nope. How about this? Nope. This? Gosh, I forgot how I did it before. Disabling the middle option seems to work. Uh, you mean this right here? But I still hear it in my ears. Um, so stream only. Hello. I'd hit something like earlier, like last time. Test. Yeah, weird. I don't know. Oh, okay. I see. What's happening here. All right. Anyway, is this working? There's like some modal window here. Close. All right. I'll mess with that later, but yeah, I have no idea how I turned the monitor off here. Audio preview, system sound, microphone. Sorry, it's like driving me nuts and I can't like hear anything. Tests, audio preview, automatic, audio preview, exclusive audio source. Yeah, this is all of this stuff like falls short. It's really sad and disappointing. Like all of the software. Okay, it sounds good. All right, cool. All right, so all right, so where were we? So we were about to try this here. So then and floors equals size dot floors. All right, so let's see. So yeah, the features. I'm just gonna. All right, so I just muted my headset. So all right, so in 32 single. Okay, so everything I apparently has to be a, a float. All right, so we're gonna enter in. Oh, but I only have like one thing entered in, so all the floors are gonna be zero. So 2.5. Yeah, floors are zero. Zero floors. That's great. Here, let's cheat and just do this. So floors, read line, and all right. So I have to do two lines. All right. So the first one is what size? So the size is going to be 1.1, and the floors are going to be two floors, 153K. So okay, so this like kind of works. So if I do like uh 8.5 8,500 square feet and I do three floors, 702K. So let's look at this. So we're just under here, we're three floors and the price 702. So why is this cheaper? Yeah, because we're 8,500 square feet. So then if I'm 1,000, if I'm 3,000 square feet and I'm three floors, 235K. Okay, so I think we all see how this works, right? Um, I think we all see how this works. Um, yeah, so I think we see how this works. What did you say? What about predicting floors greater than three outside the? Yeah, that's a good one. Okay, so let's do two for the size, so 2,000 square feet, and then eight floors. I feel like that's not right. Well, I guess they'd be really small floors, right? You're like living in a tower in like a lighthouse or something. Uh, so, oh, okay. So this was millions because I put 300,000 square feet. So that's like a warehouse. So let's do 8,000 square feet. So this is 8,000 and then four floors. So let's do seven and four floors and seven and three floors. So each floor adds like 30K over here for 7,000 square feet. Let's see. So seven and then two. So that's interesting. 7,000 on two means it's like got a wider footprint. right? Because if you're 7,000 square feet and you're there, so if I do 7 and 1 floor, it's more expensive. Why is it? Why is 2 floors? Oh yeah, yeah, because it's 3,500 feet per floor at that. So like, let's see, predicting floors greater than three, values outside the training set. Yeah. So like this kind of makes sense, right? Oops. Yeah, this totally makes sense. All right. Yeah, this totally makes sense. So let's. All right. Anything else we want to play with this one? Yeah. So it's they're gonna pay you to take a 7,000 square foot house with 30 floors. They're gonna pay you. So that goes both directions. Oh, zero and zeros. So the base price of a house is 128. Yeah, 1 floor, 0 square feet. That's interesting. Okay, so this makes sense, right? That makes total sense. So now let's. Oh, what do I have here? Do I not have this? This is driving me nuts. I'm sorry, folks. Um, combine taskbar buttons, yes. Where's the feature for only showing them on the monitor they're on? Okay, main taskbar. So taskbar where Windows open. Yeah, that's been driving me nuts. Okay, been meaning to change that for like a long time. All right. So that makes a lot of sense, right? Let's look at the next one. So I think we were in this browser here. All right. All right. So I have to switch this here. Your channel, YouTube Studio. Yeah. Okay. So now let's look over here. So let's look at some more of those samples. Oh, we were looking at those blog posts, right? Isn't that what we were doing? Yeah. So we were looking at these blog posts here. So we just did the simple exercise. So that makes a lot of sense. We create a context, we create an array of house data, we load data into memory. So you know what, while this is going, so I've never done any machine learning before, right? And so I had like all these like preconceived notions about it and like what it actually is, because nobody can seem to actually tell me what exactly it is. So again, I visited my good friend ChatGPT, and ChatGPT explained to me everything I needed to know. Now, you're previously in blah blah blah. Okay, so the one that we were talking about, and this is like an important thing. So let me. Is this the one? Oh, so I had a chat. Um, nope. They brought back like a whole bunch of stuff, and nope. This is one where I tried to get ChatGPT to generate a bitmap for me, and so like by generating the hex for me, and then taking the star image, like a 1 bit, so when a 1 bit of the star. So you see, like this is that diamond, and I had to output the bitmap with everything here. It didn't do it too well. It gave me a corrupted file with a valid header and everything, which was kind of cool. But anyway, so I don't need this one. Splitting concatenated words. Is this the one? No, this is the one that I had printed out. This is another one. I think this is the one. Yeah. Okay, so this is the one. So this is a continuation of like the carpet and carpet and all that one, right? So like, so what I did is I wanted to explore, so I extended the session, right? And I had like an hours long conversation with ChatGPT 3 about this thing. And so I'm talking about, so we went from the brute force, right? Basically asking the question, generate all the possible words that can be formed by computing substrings of the given string of letters, right? So basically, it's the best you're gonna get is like O to N complexity there, and because you have like the two loops and it goes like a long time, so you're basically brute forcing. So I said here, how can a language model help? So it actually suggested here that it actually like suggested, well, somewhere, but anyway. So I said, how can a language model help? So then it teases me and says, oh, I can help you. Um, so generating word combinations, given a string of letters, a language model can generate a list of potential word combinations. How do you train a language model? So it's the same thing. Data collection, that graphic we went through with the purple, right? So data pre-processing. So we're just like tokenization, et cetera. Model architecture, different types of models, right? Recurrent neural network and LSTM or transformer. Um, so my understanding is ChatGPT-3 is a transformer, right? So then you train, then you evaluate, and then you fine tune, right? So asked to explain, blah, blah, blah. So I'm like, it starts talking about model parameters, right? Oh, long short-term memory. Yeah, that's what LSTM is, right? So it tells me what a parameter is. In the context of the language model, model parameters refer to internal variables that the model learned during the training process. These parameters are the values that are adjusted to optimize performance of the model, right? So weights and biases it talks about, and hyperparameters. So I was like, how can model parameters be generated? Remind you, like I've never done this stuff, right? So random initialization, or you're using a pre-trained model, somebody that's already made a model, right? Key initialization. So like activation functions and all this stuff. I don't know what any of this stuff is, right? So I'm asking this. So I said, how can this be done in C sharp? So TensorFlow.net, ML.net, CNTK, etc. Right? So first step, prepare your data set, prepare it, model it, define, train, and then a beam search. They're saying we'll explore limited search, limited candidates, right? So beam search is not what we want. That's how you like can efficiently search for it, like in the prior approach. So it's talking about hidden layers and stuff like that. And I said, what's a hidden layer? It's the layer of neurons that's located between the input and the output. So it's everything in between your input and output, right? Um, so I said, what does a neuron do? And it says fundamental building block of neural networks, a mathematical function that takes in one or more inputs, performs computation on them, and produces one or more outputs. The computation performed by a neuron is also referred to as an activation function. So now we're getting somewhere, right? So ChatGPT is kind of getting into, instead of this high level stuff, it's getting in deeper to what these things are, right? And I validated a lot of this. Once I knew what to look up, I went on Wikipedia and validated so much of it. Um, so in the context of neural networks, neuron can be thought of as a simple processing unit that receives input and performs computation, produces an output, etc. Um, represented by parameters, which you learn during the training process. So I'm like, okay, so yeah, the inputs of the computation are represented by its parameters. Sure, that makes total sense. And then you learn the parameters are learned during the training process. So I'm sitting there thinking, I'm like, okay, so the neuron takes inputs that are called parameters and then uses them for computation of the neuron with the activation function. Okay, got it. But now where do parameters come from? They're learned in the training process. Well, like how exactly are they learned? The computation performed by a neuron can be simple, such as a linear combination of inputs, or more complex, such as nonlinear transformation of inputs. So that's more math stuff. I'm not a math person, right? Most common nonlinear function used as an activation function is a rectified linear unit. And then the output can be thought of as a measure of how active it is given the input. The more active a neuron is, the higher the output. The output of a neuron is then passed into other neurons, and it allows the neural network to learn different features and representations of the input data. So that really doesn't tell you much other than the higher the value that comes out, the more active it is. So I guess that's like more important, right? So what is an example of activation function? So, and this is where it all started to make sense for me around here. Mathematical function that is applied to the output of a neuron. It is used to introduce nonlinearity into the neural network, allowing it to learn and model more complex patterns. So the sigmoid, so a sigmoid function, squashing function that maps any input to a value between 0 and 1. All right. Useful for output layers that need to predict probabilities. So that would give you a bunch, like with a bunch of inputs, I guess, any values, like whatever it is, and tell you a score, right? For confidence. So the ReLU one negative value, it's a function that maps a negative input value to 0 and any positive value to the same positive value. So this is like, now I'm thinking about this, I'm like, okay, so it's almost like if you're negative, it's 0, and if you're not negative, then the value is the value that's coming out there. So it's almost kind of like an absolute, almost like absolute value, but instead it's like, um, if it's negative, it doesn't go to positive, it just goes to 0. That's kind of how I thought about it. So you got the hyperbolic tangent, which is also a squashing function, but maps input values to a range between -1 and 1. So instead of giving you a value between 0 and 1, you've got -1 and 1, which adds like 0, like a null value, and then like a negative and a positive range, right? Which is, I guess, a different way to like model something. That's kind of how I looked at this whole thing. Are you a math guy, Ame? I'm sorry, I assumed you were a guy, but are you a math person? So then softmax, a generalization of the sigmoid function that is used for multi-class classification problems. It maps input values of probability distribution all over classes. Colleagues who do ML, okay. All right, so yeah, you're more of a math person. Does this stuff like mean stuff to you? Like, does a hyperbolic tangent mean something to you? Doesn't to me. So, so I said, how does this all come together to produce text and find patterns? So I'm trying to like figure this out. Um, okay, good. Yeah, I know it means stuff, but like, does it mean stuff to you? Like, are you understanding this, right? Um, so I'm asking like the real question here, like, okay, you've told me a bunch of math stuff, but how do I take a word and find a pattern and produce text? Like, how does this all come together? Like, how does it get there? And I said, I don't understand how we go from an input prompt in English to an output in English via a neural network. And then it starts telling me about it's designed to simulate the way the human brain, all like the high level nonsense, that they kind of like gloss over. I could have read this in a CNN article or something. So interconnected neurons with process and transmit information. Gee, thanks. That's not really helpful. None of that is telling me anything except neurons take in a set of inputs, perform a computation, and produce an output. Not helpful. Okay, so when it comes to natural language processing, neural network is trained on a large data set of text. Okay, obvious. The input to the neural network is a sequence of words, and the output is the next word in the sequence. Now we're starting to get somewhere, right? Like that's kind of what I'm trying to do here, right? Um, the network's task is to learn the probability distribution of words in the language so that it can predict the most likely next word given a sequence of previous words. Okay, yes, that's like functionally what I want, right? That's like functionally what's going on here. Um, it's composed of multiple layers, each its own set of neurons. The first layer, called the input layer, receives the input, the sequence of words. Each neuron in the input layer is responsible for processing one word. The input layer is connected to one or more hidden layers. Okay, each neuron has one word. So the way this kind of made sense to me, is, oops. Okay, so if I have like, the dog is brown and the dog is hairy, right? So if this is my input, so if this was my input, right? So first, if that's my prompt or whatever, right? I guess that's what they call it. I have no idea, right? So if that's my prompt, right? So that's, I have to take this and turn this into a bunch of numbers somehow, right? So like we tokenize this, let's say simply we go word by word, and our token separator is our space, right? Um, and so all right. Um, I just lost it when I like zoomed in here. Totally just, okay, so we're here. We've done these ones already. Activation functions. All right. The network's tasked to learn the probability distribution, predict the most likely learners. Okay. Okay. Receives the input of words, a sequence of words. So if that's our input, right? Each neuron in the input layer is responsible for processing one word. The input layer is connected to one or more hidden layers, which are used for the abstract representation of the input data and learning complex relationships. So this tells me a little bit more. So this would mean to process this 1, 2, 3, 4, 5, 6, 7, 8. So we would need 8 neurons, I guess. Is that what that means? Each with its own receives the input, the sequence of words. So the input layer gets this whole thing. Then the input layer is going to take that, tokenize that, and then pass in each one of these words into the hidden layer, which is the neurons, I guess, right? It uses functions called activation functions, like we saw above, which is used to introduce nonlinearity into the model. Okay. Um, this allows the model to learn more complex patterns in the data, such as long-term dependencies. The output of the final hidden layer is then passed to the output layer, which produces the predicted next word. So now it's taking the numbers and translating it back into an English word, right? Um, so I guess the input model takes this whole piece, it gets tokenized, one per neuron, it goes all the way out, and I guess maybe it's kind of like a fork join, and then eventually you end up with the next word in the output on the output layer, right? So the output layer also uses the activation function to convert the output of the hidden layer into the probability distribution over the vocabulary of words. So my understanding is the vocabulary of words is the entire corpus of input data that ever came into it that it knows about. Um, so during the training process, the model is presented with a sequence of words and the corresponding correct next word, and the model's parameters are adjusted to minimize the error between the predicted next word and the correct next word. Yeah, we'll have to come back to that, right? So basically we're gonna say the dog is, and we want it to predict brown or something else like brown, right? Yeah, I don't know if that's the loss function, then I don't know if this is right, because there's this thing called AI hallucination where it just makes shit up confidently. So I don't know. But I researched most of this by looking stuff up in Wikipedia. So after training, the model can be used to generate new text by inputting a seed sequence of words and then repeatedly sampling the next word from the predicted probability distribution. So I could do the dog is, and it could say brown, and it might say hairy, it might say other things, right? Depending on the vocabulary and the data it was trained with. That's my understanding. Okay, so now it's like, how exactly does a neuron in the input layer process a word? that's like an obvious question. Like, how does it get there? Because it hasn't really told me like how the gets turned into a number, right? So in a neural network, each neuron represents, it keeps repeating itself, right? A single feature of the input. When processing a word, the input layer would typically represent each word as a fixed length vector of numerical values called a word embedding. All right. So these embeddings capture the meaning and the context of words in a continuous vector space, allowing the network to treat words as numerical values and perform mathematical operations on them. So like I knew what a vector was from programming, like in like C or C++ using a vector, right? Like holds a bunch of values, right? Um, and then the um, the fixed length vector of numerical values, right? So it's basically a set of numbers, right? So like my understanding is it takes the and turns it into, well, these are, so this is, if this is our vector, right? Uh, right? A three-dimensional vector, right? I think that's what that would be based on what I learned. And so this would be a word embedding, I guess, right? But there's more to it, and I asked more about it. When a word is input into the network, its corresponding embedding is passed to the input layer, where each neuron receives the value of one element of the embedded vector. Um, so each neuron receives the value of one element of the embedding vector. So each neuron would take one of these, right? And together, this I guess is a word embedding, um, I guess. But then the neuron performs simple mathematical operation on the input, such as a dot product. So dot product of all these guys with a weight vector and an optional bias term, and applies an activation function to the result. This produces a new output value that represents the input word, but with some nonlinearity added, right? So like eventually this gets turned into something like that, right? Is this making sense to you? Um, and passed to the next layer. In this way, the neural network takes the input words, processes them through multiple layers, and learns to find patterns between the input and output. The output layer will be connected to the last hidden layer and will produce the final output in a natural language. So then eventually, this gets turned into dog somehow, right? Like, so I said, what does a word embedding look like? And then it talks about it's a way of representing words as numerical vectors, right, in a high dimensional space. So this is three-dimensional. So this is just going to go on and on and on with many dimensions. Um, Generated by training a neural network on a large corpus of text. The input of the network is a one hot encoded representation of the word, and the output is a dense vector, usually with several hundred dimensions. The network is trained to predict the surrounding context of a word, giving the word itself as input. This process is called word-to-vec. Um, One way to visualize a word embedding is a point in a high dimensional space where each dimension represents a different semantic feature or concept, right? So in our problem before, not sure if it's discretizing the letters or simply treating the word as an atomic object. So I actually asked that question. I asked a very similar question. If I'm understanding what discretizing is that like the word discrete? Like, is it unique? Yeah. No, that's different, right? Represent or approximate quantity using a discrete quantity or quantities. Not helpful. Um, in applied mathematics, there we go. So this is like what I did like for several hours. So splitting it up, process trying continuous functions models and equates into discrete counterparts. Now, does it mean like, yeah, unique, right? like distinct, right? Is that what they're kind of saying here? Yeah. Okay. Yeah. Yeah. All right. So they could have just said that. Um, all right. High dimensional space where each dimension represents a different semantic feature or concept. Words that are semantically similar will be close to each other in this space, while dissimilar words will be further apart. So what this made me think of, um, let's see, Wolfram Alpha, right? Let's see. So what this made me think of is, so um, plot uh, this vector. So I'm expecting like a Cartesian space kind of thing, right? So this, um, maybe plot's the wrong word. Yeah, well, there's a point, right? And I don't know. I don't know. You tell me, man. Yeah, okay. So we went from two-dimensional space to three-dimensional, and now we add a fourth dimension, and I guess it can't plot in four dimensions. I don't know. Um, but anyway, so the way I kind of understood it was, okay, what happened to this thing? It used to do like really cool stuff. But anyway, so what I kind of understood this to mean was you have this, and then you have things that are similar together, words, word embeddings that have similar semantic features or concepts, which are these values inside of a vector, in this high dimensional or n dimensional vector, where each dimension is a different feature in dimensional space. And I like here. So for example, the words king and queen might be close together in the embedding space, while king and car would be further apart. So I thought of this as, if you were to plot in n-dimensional space all of the points within the vector, all of the features, things that are more related would be physically closer together in the dimensional space. Like in their example, king is close to queen. So like, let's just pretend, king looks like, the word embedding for king looks like this. Um, right? And yeah, let's just pretend it looks like that, right? So it might be, if you were to plot these, and I'm just gonna pretend that making numbers that are similar to them. So these are probably closer, I guess. Um, just as, I guess an easier example is 1, 1 and 0, 1 are close together in three-dimensional space, in two-dimensional space, or here, if we do, so these, I don't know. Let's see. Let's try and see if it will do this. Plot vectors. Will it do two? Okay, and then yeah. So it's, let me enlarge. Ah. Um. So let me do a thing that's closer to it. So 5, 5, 5. Yeah. So the last one would be car. So king and queen are close together in the dimensional space, and then car, which I'm pretending is the last one, is further away, right? Is this making sense? I think they would be close because of the training data. Yes, they would be close because the features of them, one of the features might be like a distance in the sentence. So like the is position 1, 2, 3, 4, the fourth word, right? And so brown is one away from dog, and hairy is also one away from dog. So the one word away has been brown and hairy. So those could be thought of as a different feature, right? But learning the word brown would mean in different contexts, like in things like colors or stuff like that, I guess, you would have different features. And that's where you get like, I guess that's where you would have like a feature that means brown, right? And then you'd have another feature of brown's relationship to black and to red, because they would be like a cluster of colors, right? Like that's my understanding of this whole thing. Okay, and I can't read this chat, so I need to um, make this a little bit less opaque. No, less opaque. Uh, Reset opacity, yet it's still not opaque. I don't know what the point of having this background fill color if it doesn't like actually do anything. Um, okay, anyway. There we go, dynamic range. What's the S to? So that's my understanding here, where things are close to each other in that dimensional space. Um, so it's also possible to use pre-trained word embeddings that have been generated using large amount of data and fine-tuned them to specific task or domain. This is called transfer learning. Okay, yeah, got it. But like I wanted to, so I say, what's a one hot encoded representation of a word? Right? It's a method of representing words in a vector format where each word is represented by a vector of the same length as the size of the vocabulary. And the vocabulary, as I learned, is all of the words it's ever known, right? To the brown hair relationship versus the and dog. Oh, yeah, yeah, yeah. Exactly, exactly. So it would know brown as a color because it already has it. Brown has its own word embedding with relationships from like red, green, blue, black, because the input, the training data, um, the corpus, right, that was used to build the vocabulary, that had a bunch of colors and stuff about colors, right? So that's how it learned colors. It doesn't actually know colors. It just knows that these things are related to each other by some numerical representation. That was my whole understanding, and it's basically a bunch of bullshit, randomness stuff. And I actually asked this, but you'll see. So I needed to learn more, right? So each element in the vector represents a possible word in the vocabulary, and the element corresponding to the actual word is set to 1. The element corresponding to the actual word is set to 1. So maybe that's the first one. So like in our example, so this would mean 1, right? Oops. So this would mean 1, and like then there's like features, right? I guess. Um, while all other elements are set to 0. This, I don't know why that's like that, right? While all the elements of this encoding method is often used as the input layer of neural networks for natural language process tasks such as language translation, sentiment analysis, blah, blah, blah. One hot encoded vector serves as a way to represent the words in numerical format so that the model can understand and work with. Oh, okay. So what they're saying is now let's clarify this, right? So what they're saying is if you have if you have a 5 feature model here, right? 5 parameter model, right? Your first one, your initial, so 1, 2, 3, 4, 5, right? So that's what they're saying. The features are uninitialized. And I think what they mean here is the element corresponding to the actual word is set to 1. So if we say that the nth, so if we like encode this here, I think it's like word. So word and word to precede. Oops. So word and preceding. Oops, no, preceding word, and then next word. Um, next word to. um, right? Well, another way to say it is like word position minus one, and then and relative to the word's position, right? So this would be like minus two, so the word before it, and this would be word position plus one, 1, 2, 3, 4, and 5, right? So so these would be 0, right? And now if the is this and dog is this and dog and is and brown, uh, yeah, so this is what we tokenize, and this would be like our input, right? I think, right? Because and this is what it would represent. So basically, the word the is 1, dog is 2, is 3, and brown is 4, right? And then so that's what it would look like in our vocabulary, I think, because like in just a list of words, right? Without any other like data associated with them. This encoding method is used to input layer of neural networks for neural natural language processing, such as language translation, blah, 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 blah. Serves as a way to represent words in numerical format that the model can understand and work with. Okay, so now if you have a list of words, I think what they're saying here, um, so so now if we were to take it this whole sentence, right? So if this is our vocabulary right here, right? If that's our vocabulary and this is our list of features. So if this is like the key to the meaning, the concept associated with each element in the vector, right? So if that's this, so then if the input is the dog is brown, right? Then we tokenize the words as I'm guessing at this. I really don't know. So word position minus one is that one. Um, So we can do -1 here because there's nothing, oh, 0 because there's nothing there, right? So there's nothing, word -1, word -2, but now the word +1 is going to be 2 for dog from the vocabulary, and then is going to be that, and then dog is, so the word -1 is going to be the word -2 is going to be 0 because there's nothing before it. And then word +1 is going to be is, and then 4. And then, so now is word -1 is going to be dog. The is going to be there. And then is 1, and then word +1 is going to be brown, which is 4, and there's nothing past it, right? Um, and then brown is going to be, brown -1 is going to be 3 for is, -2 is dog, and then there's nothing preceding it. So I think this is right based on what I'm understanding. So this is what a word embedding in the context of this vocabulary with this set of features. So the first index in the first element 1 in the in the vector is the word itself, which we're saying in our vocabulary is like this with all of our features, right? And then word -1. So I think we're saying the feature of this word in the context of this input is this. I think that's what's happening. Serves as a way to represent in numerical format the model can understand and work with. So I think we've just done that, right? So what are some of the features and concepts of word embedding? So it repeats itself. Low dimensional. Okay, some of the features or concepts include low dimensional. Unlike one hot-coded representations, which can be high dimensional, word embeddings are typically low dimensional and usually on the order of a few hundred dimensions. So I think this is like them saying that there's like going, 100 forward and 100 back potentially, I think. Um, and I don't know what other features of these words. Oh, might be a part of speech, for example. Yeah, so like this might be part of speech, and the is oh God, I hate English, right? So this is a noun. Uh, yeah, I'm just gonna make this up. Participle uh, is I don't know. I don't know. And then this is a brown is a noun and an adjective, right? Person, place, or thing. A thing can't be brown, so that's an adjective, right? And I know there's more like um, parts of speech, but this is like what I remember because I haven't had to break this down since like fifth grade. All right, so low dimensional, um, continuous. Unlike one hot code representation, which are discrete. Um, Oh, yeah, which are discrete. Word embeddings are continuous, meaning they can take on any real value within a given range. All right, so real value, they're talking about real numbers, I think here. Article. Yeah, I don't know either, man. I don't know. Yeah. All right, distributed. Unlike one hot encodings, which is vector to the words. Is this making sense? I think this is what they're saying here. I should probably take that MIT Open Courseware one with the dude who does all that Google AI stuff. Forget his name. Anyway, dense. Unlike hot one coded representations, which are sparse, um, word embeddings are dense, meaning that most of the values in the vector are non-zero. Yeah, exactly. So this would be denser than this set of vectors. Okay. Uh, Learned. Unlike one hot encoded, which are often arbitrary. Yeah, that was the part that kind of like the one hot coded reference often arbitrary. Word embeddings are learned from data using techniques such as neural networks. Meaningful word embeddings are able to capture the meaning of a word and its context of similar words with closed in vector space. So I think this would be a meaningful um, word embedding here, right? I think that would be a meaningful one, is what they would call it there. So word embedding is every possible relationship between input word and every other possible value from the data corpus. So I'm like, it's how this one thing relates to everything else in its known universe. So mathematical representation of a word in continuous vector space where each dimension represents a feature or concept of the word, which is what we've done here, right? Um, the goal of word embedding is to capture the meaning of a word and the relationships it has with other words in a way that can be useful for natural language processing tasks. Yes. So this was my takeaway of this whole thing. Um, so then it talks about this binary vector with the same length as the vocabulary with a single one in the position. So that would mean that if our vocabulary is 1, 2, 3, 4, then you would have one, one, 1, 2, 3, 4. Yeah, I think that's what that would mean in the one hot coded representation because it's n dimensional, or n is the size of your vocabulary, I guess. Um, where with a single one in the position corresponding to the index of that word in the vocabulary and 0 everywhere else. Oh, oh. So it's not 1 here, and it's not 2, and it's not 3, and it's not 4, right? So if your vocabulary is the dog is brown, so 4, so 1 is going to be here, the rest are 0. So this would be here, and this is here. So there's apparently a ready way to do this, right? And then this would be 0, and this would be 1. So I think that's what this means, right? This would be a sparse matrix, set of matrices. I don't know. I should go read a math book or something. Um, but the representation is very high dimensional and highly dimensional and sparse, and doesn't capture any semantic or syntactic relationships between words, which makes it difficult to use for NLP tasks. So this is a list of words, right? And the size of the dimensions of the one hot encoded representation is where it is on the vocabulary list. Okay. On the other hand, by the way, I just learned that the other day, the whole like, what is a dense and sparse matrix? I just learned that when I was validating what ChatGPT here was telling me. All right, so words by using a technique such as set of unique words or tokens that the model is aware of and can work with. During the training phase, model is exposed to large corpus of text, creates a vocabulary, extracting all the unique words and tokens from that text, right? Then it's used to create word embeddings, which are numerical representations. So it repeats itself a lot, right? The size of the vocabulary will determine the number of input neurons in the input layer of the neural network, and the typically excuse me, typically in the hundreds or thousands of dimensions. Each dimension of the vector would represent a different feature or concept of the model has learned to associate with the word cat based on the training data. For example, one dimension might represent the concept of small domestic animal. Another dimension might represent concept of 4 legs. Another might be concept of meow, which takes it like much further than just like part of speech and stuff like that, right? Um, exact values would depend on the specific model and training data used, but the vector would be fixed for a given model and word. So like when I was reading this for the first time, I was like, oh, I understand now. Like it's kind of all coming together that what's kind of like in the back of my head when I'm reading this for the first time was, okay, so the words themselves don't really matter. The English words, the English meanings don't matter. They're just consistently encoding. Oh, what happened? You gotta go? Oh man, it's 2 a.m. by me. I should go to sleep. I got work and stuff to do tomorrow. All right, well, I'll do a little bit more because we're at a good part here, right? Um, Word embeddings are a powerful tool, and this tells me like nothing here, right? Okay, back to word embedding, storing concepts related to input words. Is a model really just a list of concepts? In a way, yes. A trained language model is essentially a complex function that takes in an input such as a word or sentence and maps it to a set of outputs such as predicted next word or sentiment score. Model learns to do this by mapping training on large data sets of inputs and corresponding outputs, and encodes its understanding on the relationships between inputs and outputs in the form of a set of parameters, which can be thought of as a list of concepts. These concepts are represented in the form of word embeddings and other internal representations, which capture various aspects of the input, like the positioning and stuff like that, and like part of speech, and the relationships between different inputs. So each dimension in a word embedding is another word embedding. Note each dimension is a word embedding is a feature or characteristic of the input word. In other words, it represents a different aspect or property of the input word. A word embedding is a multi-dimensional vector, blah, 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 same thing. It repeats itself. Yeah, so the size of the vector is usually much smaller than the size of vocabulary. And model training is really just generating the definition of the dimensions. Oh, okay. What was the last thing you heard? Because I'm dual streaming. But oh, yeah. So basically, what I was saying was that word embedding is basically a feature, is a characteristic. For cat, one might be a small domestic animal, 4 legs, the concept of meow, like those types of things. Um, so then I go back and I'm like, okay, so is it just another word embedding, trying to figure out like what is it really trying to say here. Um, so multidimensional vector, it keeps repeating this, like it's gonna keep making sense to me if it keeps repeating itself, right? Um, now here's where